Hi, in this video, we are going to continue our problem solving sessions. Today, I have 4 problems from RMO 2023. So all of these problems are RMO 2023, so last year's Regional Maths Olympiad. This is problem 111. This says, let n be the set of all positive integers and S is equal to the 4-tuple ABCD belonging to the space of positive integers such that a square plus b square plus c square plus d square, a square plus b square plus c square is equal to d square. We have to find the largest positive integer m such that m divides ABCD for all ABCD belonging to S. So S is the set of positive integers which satisfy the condition a square plus b square plus c square is d square. And we have to find the largest integer m which divides ABCD, the product of these 4 integers, right? So since we have squares here, it makes sense to think of a, b, c, d modulo 4, the quadratic residues of a square, b square, c square, and d square have to be either 0 or 1 mod 4. If you are unfamiliar with quadratic residues, I recommend that you check out my number theory course on Udemy. I have a detailed discussion of that on Udemy. So you can look at it and there is a description of that there. So a square, b square, c square, d square must be 0 or 1 mod 4. Now, if you think of the possibilities for a square plus b square plus c square is equal to d square, now this d square could be 0 or it could be 1 mod 4, right? If d square is 0 mod 4, the only way you can have a square plus b square plus c square is if each of them are 0, 0, 0 mod 4. All of it we are looking at modulo 4. If d square was 0 mod 4, you have to have this and this and this as 0. Because if any one of them is 1 mod 4, then overall the sum will not be 0 mod 4. If d square was 1, however, you could do it in 3 ways: 1, 0, 0, 1, 0, 1, 0, or 0, 0, 1. And in all these 3 cases, d square is 1 mod 4. So basically, I am looking at possibilities for ABCD modulo 4. We are getting that a square, b square, c square, and d square can be only 0 or 1 mod 4. And these are the 4 possibilities, 4 cases, right? Now think about it. In all of these cases, we have at least two of a square, b square, c square, d square must be 0 mod 4. If at least if any of them is 0 mod 4, if a square is 0 mod 4, it implies that a must be 0 mod 2. Basically, a is even, right? So similarly, if b square is 0 mod 4, b must be even. So basically, 2 of them are even at least. And 2 of them are even means that the product ABCD is divisible by 4. If you take ABCD, we can say that 4 must divide ABCD because 2 of ABCD must be even, right? Okay, so we have figured this part out. Now let's look at a square, b square, c square, and d square modulo 3. If you look at the quadratic residues for mod 3, the only possibilities are 0 or 1 again, mod 3. So how can we get the relation a square plus b square plus c square is equal to d square? If this is 0, this could be 0, 0, 0, or it could be 1, 1, 1, right? And if this is 1, then you have the normal 3 cases. These are the 5 possibilities in this case for a square, b square, c square to be 0 or 1 mod 3. These are the 5 ways in which this relation will be true, right? So in each of these cases, you can see that at least one out of a square, b square, c square, and d square is congruent to 0 mod 3. So that means a square is divisible by 3. That means this implies that a is congruent to 0 mod 3, right? So basically, the only way in which this condition is satisfied is if at least one of them, A, B, C, D, is divisible by 3, which means that 3 divides A, B, C, D. We already have 4 divides A, B, C, D. This implies that 12 divides A, B, C, D, right? So what we know is that we have to find the largest positive integer m such that n divides ABCD. So one candidate integer for us is 12 by the way, right? So since 12 divides ABCD, we should have m should divide 12 for sure, right? I'm making a mistake here. I should be saying that 12 should divide m. 12 is supposed to divide ABCD. So largest positive integer m, 12 should divide m here. 12 is a factor of ABCD, so 12 should divide m here. And now what we can say is if m divides ABCD, that implies that m is less than equal to, if m divides ABCD, one of the candidate values of ABCD which satisfy this equation is 1, 2, 2, and 3. A is 1, B is 2, C is 2, and D is 3. And in that case, you get a square plus b square plus c square is equal to d square. And in this case, we have ABCD is equal to 12. And note that the question said that we have to find the largest integer m such that m divides ABCD for all values of ABCD. All values of ABCD satisfying S. So one particular set of values of ABCD is 1, 2, 2, 3. And in that case, ABCD is 12. And if m divides ABCD, we get m divides 12. So if m divides 12 and from here we get 12 divides m, that implies that m must be equal to 12. That is a common way to prove equality in number theory. If a divides b and b divides a, then a is equal to b, right? So this also means that m must be less than equal to 12, right? So there is no other possibility of m that we can consider actually. M divides 12 means m must be less than equal to 12. So because we got this one case, 1, 2, 2, 3 satisfying this result, we ensured that m must be such that it divides 12. So m must be less than 12. And from the other side, we have gotten already that 12 divides ABCD, so 12 divides m. So now we get the equality. So that was the first problem. This was number theory problem from last year's Olympiad. Let's look at another question. 112. Let n be greater than k be greater than 1 be positive integers. Determine all positive reals a1 a2 to an that satisfy that satisfy this inequality, summation of I goes from 1 to n root over k ai power k by k minus 1 ai power k plus 1 is equal to summation of I goes from 1 to n ai is equal to n. Okay. We have to find all positive reals that satisfy this equality. Now think about it. This expression is a little complicated. We'll try to set up an inequality on the denominator here. So we can say k minus 1 ai power k plus 1 is the same thing as ai power k plus ai power k. And this is going to be added k minus 1 times plus 1. And we know that k and ai are all positive. So we can apply AMGM on these overall k terms. So we can say that this will be greater than equal to k times kth root of ai power k times ai power k and so on, ai power k times 1. And this has been repeated k minus 1 times. So if you think about it, the quantity inside the radical will become ai power k to the power k minus 1, and you have to do kth root of this. So this will come out to be ai power k minus 1, and there is a k outside. So what we have shown here is that the denominator is greater than equal to k times ai power k minus 1, right? Great. So we'll use that to set up an inequality here on the LHS, this term, right? So we'll say summation of k goes from 1 to n square root of k ai power k by k minus 1 ai power k plus 1. Now we know that this term is greater than equal to what we found out in the previous screen, k times ai power k minus 1. And because it is in the denominator, the inequality, if you replace it with a smaller quantity, this is going to be lesser than equal to, right? Because k minus 1 ai power k plus 1 is greater than equal to k ai power k minus 1. So we are going to say now this is less than equal to summation k is equal to 1 to n square root of k ai power k by k ai power k minus 1. I have replaced this with this and used this inequality to write this result, right? So this gets cancelled and this is equal to summation k goes from 1 to n root over ai, right? Great. So we have this, and this is basically looking like root a1 plus root a2 and so on till root an. We can apply Cauchy's inequality to this. So we are saying root a1 into 1 plus root a2 into 1 plus root an into 1 will be less than equal to square root of 1 square plus 1 square n times, and root a1 square plus root a2 square is a1 plus a2 plus an. So we know that this quantity is less than equal to root over n times, this is summation of ai, where I goes from, right, I goes from 1 to n, right? Correct. So this quantity, which was summation of k goes from 1 to n, I have written the summation wrong here, by the way. In all of these steps, it was summation over I. I made a mistake in writing. I goes from 1 to n, right? So this is also summation of I goes from 1 to n root over ai is less than equal to, I'm getting root over n times summation of ai, where I goes from 1 to n. So here we can write this as less than equal to root over n times summation of ai. I goes from 1 to n. So what is the overall thing looking like to us? Let's write all the results we have gotten so far. So the LHS was summation I goes from 1 to n root over k ai par k by k minus 1 ai par k minus 1 ai par k plus 1. We got that is less than equal to summation of I is equal to 1 to n root over ai, and that is less than equal to root over n times summation of ai, where I goes from 1 to n, right? Now, in the problem, it has been said that this thing is equal to summation of I goes from 1 to n ai, which is equal to n. So how can this quantity be equal to this, right? So what we are getting from here is summation of ai is less than equal to root over n summation of ai. I goes from 1 to n. So if you call this as s, you are getting s is less than equal to root over ns. So you're getting s square is less than equal to ns, and you're getting s is less than equal to n, right? But the third part of it also says that s is equal to n. Here, this is s and s is equal to n. And here we are getting s is less than equal to n. The only way in which this will happen is if s is equal to n actually and all the ai's are 1. All ai's are 1. So basically a1 is equal to a2 is equal to a3 till an is 1. If all the ai's are 1, the AMGM inequality will also give the equality case and the Cauchy's inequality will also be equal. So this is the solution for this problem. We have established a couple of inequalities. We once did a simplification using AMGM and then use Cauchy's inequality to basically get a condition that S is less than equal to NS and S is less than equal to N. And from there, and the problem has already given us that S is equal to N, implies that all the AIs must be 1 and must be equal. Okay, let's look at another problem. This is problem 113. This is also RMO 2023. This says that the side lengths of triangle ABC are positive integers, and the side lengths are denoted by small a, small b, small c. Let T of n be equal to a plus b plus c to the power 2n minus a minus b plus c to the power 2n minus a plus b minus c to the power 2n plus a minus b minus c to the power 2n for any positive integer n. Positive integer n. We have if T2 by 2T1 is equal to 2023 and A is greater than B is greater than C, determine all possible perimeters of triangle ABC. That is the question. Now, obviously, this question implies some simplification is required. T2 will look like a plus b plus c whole power 4 minus a minus b plus c whole power 4 minus a plus b minus c whole power 4 plus a minus b minus c whole power 4. If you simplify T2 and T1 and calculate this, a little bit of algebra has to be done. You will realize that T2 will come out to be something like 4bc 6a square plus 2b square plus 2c square, and 2T1 will come out to 8bc. 2T1 will come out to be 8BC. You have to check that calculation, and T2 by T1 you have to calculate. So it turns out that T2 by 2T1 is equal to 3A square plus B square plus C square. And in the problem, it was mentioned that it is equal to 2023. So we have to solve this equation where A, B, and C are positive integers and A is greater than B is greater than C, right? So if you think about the quadratic residues of A square, B square, C square modulo 4, you will realize that this side is 3 mod 4, 3 mod 4. So we can get this by saying that this is A square is 1 mod 4 and B and C are 0 mod 4. If you try anything else, for example, A square is 0 mod 4, then B and C could be 0 or 1 and they will not be able to add up to 3 mod 4. So this is the only possibility because quadratic residues modulo 4 are only 0 or 1. So this is the only possibility that we have, right? So what we know right now is A square is congruent to 1 mod 4. B square is congruent to C square is congruent to 0 mod 4. Okay. So we also know that A is the biggest side, B and C are the smaller sides. So we can write B square plus C square is equal to 2023 minus A square minus 3A square. And because the right hand side here 2023 minus 3A square must be greater than equal to 0, you can easily solve this and say that A must be less than equal to 25. And after you get this, you can start saying that check all the 1 mod 4 candidates for A less than equal to 25. When you check A is equal to 25, you will not be able to get B and C such that this happens. You can check values. B and C should be even numbers such that this is true. 3A square plus B square plus C square should be 2023. That won't happen for 25. There is no solution. But then when you check A is equal to 23, you will immediately be able to see that B and C, B could be 20 and C could be 6. That is a possible solution. Also, you have to check lower cases also, but you also have to realize that triangle inequality should always be true. So B plus C should always be greater than A, right? So you cannot make B and C too small, right? You need to satisfy all the 3 triangle inequalities also. A little bit of checking will convince you that this is the only solution for this particular case. And in that case, the perimeter of the triangle becomes 23 plus 20 plus 6 or 49. And that becomes your answer. So a little bit of casework is required and you have to look at quadratic residues again. So it looks like a problem on triangles, but actually it's a number theory problem again. Okay, let's look at the next problem. Problem 114. This is also RMO 2023. It says, let fx be a quadratic polynomial with real coefficients. Suppose that for some pairwise distinct reals A, B, and C, we have f of A is equal to BC, f of B is equal to AC, and f of C is equal to AB. We have to determine what is the value of f of A plus B plus C. Okay, so these 3 conditions can be utilized to figure out something about the polynomial. We have these 3 f of A is BC, f of B is AC, and f of C is AB, we take advantage of the symmetry here and write A times f of A is ABC, B times f of B is ABC, and C times f of C is also ABC. So this implies that A f of A minus ABC is 0, and similarly B f of B minus ABC is 0, and C f of C minus ABC is 0. Which means that if I construct a new polynomial which is x f of x minus ABC, this polynomial has three roots A, B, and C, right? This is a standard approach for polynomial interpolation. So we are trying to get this new polynomial. We are constructing this polynomial. So x f of x minus ABC has three roots. So therefore, x f of x minus ABC can be written as k times x minus a, x minus b, x minus c. So here we have to first find the value of k. So let's think about it. X f of x is equal to k times x minus a, x minus b, x minus c plus abc. And therefore f of x is equal to k times x minus a, x minus b, x minus c plus abc divided by x. So now we knew that it was a second degree polynomial here, second degree polynomial. So what constant k will make it a second degree polynomial? Think about it. If k is equal to 1, then when you factorize this out, you get a minus ABC, which cancels the plus ABC, and there is no constant term in the top, right? And since there is no constant term, what happens is divide by x makes the cubic polynomial into a quadratic. However, if k is equal to 2, 3, or any other real number, you will have a minus k ABC plus ABC. And this term will not vanish. So when you divide by x, you will have this term, and which makes fx to not be a polynomial. To not be a polynomial. A polynomial cannot have x as negative power. Here x is having a power of -1. That is not possible for a polynomial. So any value of k other than 1 makes this last term not get cancelled. So you will end up with a divide by x term. So therefore k must be 1. So therefore f of x is x minus a, x minus b, x minus c plus abc divided by x, right? So now we can easily find the value of f of a plus b plus c. F of a plus b plus c would be putting a plus b plus c into it, you get b plus c plus a plus b plus abc divided by a plus b plus c. And we can simplify this a little bit if you can factorize the top part. So if I try to factorize the top part, you will get this ca plus a square plus bc plus ab plus abc, which is the same thing as a square plus a times b plus c plus bc, and outside there is a b plus c plus abc. And what I'll write it as a square b plus c plus a b plus c b plus c plus bc b plus c plus abc. So in these two terms, I can take common a into b plus c. I get a plus this b plus c. And in the second two terms, I take a common bc and I get b plus c plus a. And finally, I can take a plus b plus c common from both of these, and I end up getting ab plus ac plus bc. So the factorization of the numerator here is a plus b plus c times ab plus bc plus ca, and you divide it by a plus b plus c, and you end up getting f of a plus b plus c is ab plus bc plus ca, which is the solution of this problem. So we have Solved it by constructing a new polynomial x f of x minus abc with roots a, b, and c. And that's a standard trick for such polynomial problems, which you should be aware of. That concludes our video. I wanted to show you these 4 problems from last year's RMO. We'll continue in the next class with more problems from RMOs. So stay tuned and hopefully you learned something from this video. If you're new to the channel, please subscribe to the channel and like the videos. You'll get a lot of content for Math Olympiads and JEE here. So hopefully you'll benefit from it. Please also press the bell icon for notifications that will help you know when a video is released. That's it from now. I'll see you next time.